Okay, so vectors and scalars. Now I'm pretty sure that most of you know or have some idea as to what vectors and scalars are, right? We know that most of the physical quantities out there can be either categorized as vectors or scalars. But there are certain quantities, and you will see those quantities in this class, which are neither vectors nor scalars. So if you already know what a stress is, what a strain is, you know that it is actually not a vector or a scalar. It is what you call a tensor quantity. Okay, so when you take strength of materials class, you will learn about different kinds of stresses, but you will learn about at least some kinds of stresses in this class as well. Scalars, you know, require a specification of just one number, which we call magnitude, right? And we have multiple examples of those. We have some things like mass. If you want to specify the mass of an object, you can say the mass of this object is 5 kilogram or 5 pound mass or 5 slugs, and you're just giving one number to specify that quantity, right? Similarly, you have things like volume, area, density, work, energy, pressure, distance. All of these are what are known as scalar quantities, because specifying them requires just specification of one number along with a unit if it is a dimensional quantity. If it is not a dimensional quantity, then it has no units in. Vectors, on the other hand, require specification of two things. One is a number, which is the magnitude, and the other is the direction. Okay, and some of the physical quantities naturally have both the information. So when we talk about, you know, velocity, right? I say I'm driving my car on Long Island Expressway at 55 miles an hour. To truly tell the velocity vector information, I have to also say something about which direction I'm going in. So I might say I'm going in the direction of New York City, okay, at any given instant. So as long as I specify both the speed, which is the magnitude part of the velocity, and the direction I'm going in, I have specified the full vector quantity. If I don't specify one of them, then I'm not specified the full vector quantity. So velocity is one example. Acceleration is, of course, another vector, because acceleration is obtained as the derivative of velocity. So those of you who are taking calculus already know what a derivative of a quantity is. You have force, which is also a vector quantity because it requires both direction and magnitude. Moment, which we'll talk about. Displacement should not be confused with the distance traveled. Distance traveled is a scalar quantity. Displacement has information about what the magnitude is as well as the direction of the displacement. Okay, and you know, momentum, angular momentum, linear momentum. There are lots of quantities that can be classified as vectors. Now, having direction and magnitude both is a necessary condition for something to be a vector, but it is not a sufficient condition. Now that may come as a surprise to many of you, because you probably thought the definition of a vector was that a quantity has both direction and magnitude. It turns out there are certain quantities out there that seem to possess both direction and magnitude, but they are actually not vectors. Okay, and we'll talk about, you know, some of those quantities, and I'll show you why they're not vectors. So the thing to remember, especially from this slide, is that just having direction and magnitude is not a sufficient condition for something to be a vector. So, for example, electric current. Okay, electric current seems to have both direction and magnitude, right? You know, if I have a wire, I lay it down like this, I could say there is a 5 ampere of current passing through this wire, and whichever direction I lay this wire in, that will become the direction, right? Road signs, finite rotation, they all seem to have both direction and magnitude, but none of them are vector quantities. And the reason they're not vector quantities is this law. They don't satisfy this law. Okay, so if you take a vector algebra, linear algebra, or abstract algebra class in maybe math department or applied math department, you will learn, if not in one of our ME classes, you will learn that vector quantities need to satisfy one of the 8 axioms. And this is one of the 8 axioms, so I'm not specifying all of them. This is one of them. This says that if you take 2 vector quantities, and notice how we are writing the vector quantities. This is important. We write a symbol and we put an arrow on top. So this is what we call a full arrow, okay? You can also have half arrows, and you will see me sometimes actually drawing arrows as half arrows because I'm in the habit of doing that. So this is a half arrow, and that's also a vector quantity. In your textbook, you might see things written like this, a bar on top. That's also a vector quantity. Some other textbooks may write the same vector quantity in bold, okay? So they'll do bold. Of course, it's hard for us to do bold, so we put an arrow on top, right? So if something is a vector quantity, there should be some visual indication that it is a vector quantity. If you do not show the arrow or a bar on top, it is assumed that you're writing a scalar quantity. And there's a big difference between the two. So if you simply write a plus b equal to b plus a or something like that without an arrow or bar on top, people will think you're writing a scalar equation. and that'll be wrong. Okay, and that's not something that we will tolerate in this department. Okay, so you need to get in the habit of showing the arrows or the bar on top of the symbols for the quantities that are actually vectors. So coming back to this law, right, this is called law of commutativity for addition. Now if you look at this, this may seem like very strange to you, right, because until now you have probably encountered numbers which you could add in any order and the final result is always the same. So if you take 3, add 5 to it, it doesn't matter which way you write it. 3 plus 5 is always equal to 5 plus 3. Answer is always 8, right? So if you add to integers, to real numbers, to rational numbers, they don't depend on the order. But it turns out that there are quantities that actually don't satisfy this property. Now, the quantities that don't satisfy this property, even if they have direction and magnitude, will not be called vector. And that's the take-home point. Okay? So quantities that can be called vector should satisfy this law. And this provides the necessary condition for a quantity to be a vector. Apart from having the direction and magnitude, they should satisfy 8 axioms, one of which is this one. And I'm only writing only one of those because you will see that most of the quantities that seem to possess both direction and magnitude don't satisfy this particular axioms. Right? Let's look at an example. So road signs, right? Think about what road signs are. Now this is one kind of road sign. There are other road signs too, like stop sign and all those. We're not talking about those. So a road sign which has maybe an arrow shown to indicate some sort of direction for turning, along with a speed limit. Okay, so we have a right turning arrow and the speed limit is 30. We have a left turning arrow, speed limit is 30. So clearly this particular sign seems to have both direction and magnitude, right? The question is this a vector? Okay, so let's say this is A, this is vector A. Assume that this is a vector, right? This is vector A and this is vector B, right? So you can add vector A with vector B, which in real world would be like taking first a right turn and then taking a left turn at the posted speed limit. Yeah? Or you could do B, which is this, and then add A to it, right? So you take the left turn and then you take the right turn at the speed limit. Tell me, will you get to the same destination starting from the same point? You won't, right? So you can easily see that. So if let's say you start somewhere here, all right? So you first take the right turn at 30 miles per hour. So that's A. This is A. That's what we are doing. And then we take a left turn. So we get over here, right? So that's B. On the other hand, if I do B first, which is this, so I will start again the same place, and I'll take a left turn, and then I'll take a left turn, and then I'll take a right turn. I get over here. Right? So clearly, if you do A plus B, which is not same as B plus A because your final answer is not same. You're not leading to the same destination, which means that road signs are not vectors. Another example, finite rotations. So what are finite rotations? Well, you could take an object and rotate it, right? Now you can associate in direction and magnitude with the rotation. So I could take this object and rotate it by 90 degrees, and I could say that I have rotated by 90 degrees about an axis that is perpendicular to the plane of this remote, right? I could say that. So I have clearly specified a direction of rotation and magnitude of rotation, which is the angle of rotation, right? So if finite rotations are vector, they should also satisfy the commutativity property, which is that A plus B should be equal to B plus A. So now to prove that vectors are not, that rotations are not vectors, all I have to do is present an example which shows that A plus B is not equal to B plus A, and I have proved that finite rotations are not vectors. So let's say we have this object, right? And we will attach a reference frame to it. We'll say that this is the x-axis. So this x-axis is in the plane of this block, which is Tinkercad. And y-axis is in the plane too, so it's basically going away from you. And z-axis is perpendicular to the plane. Okay, so it's pointing up, right? So I'm not showing y because y is kind of hidden behind the z, but it's there, right? Okay, so let's say our vector A is rotation about z-axis by 90 degrees, right? So rotation about z-axis by 90 degrees. So if you rotate about z-axis by 90 degrees, and anytime when I say 90 degree or any angle without a sign in front of it, that rotation is assumed to be counterclockwise. So convention is counterclockwise rotations are considered to be positive rotations. Okay, so about z-axis, if you rotate by 90 degree, what will happen to y? Y that was going this way will be pointing this way, and x will be now that way, right? So z-axis remains same because you're rotating about z-axis, and that's the configuration. Okay. Then we will consider another rotation, which is b, and that's a rotation about x-axis by 90 degree. So now what we'll do is we'll do the b, and that essentially would amount to doing a plus b, right? So now the rotation about x-axis, which is pointing that way, 90 degree, will bring y that way up and z this way, right? And you can do this. When you go home, you could take your book, and then you could attach x, y, z axis to it, imaginary x, y, z axis, and then do these rotations. And you can pick whatever you want, right? It doesn't matter whether you pick z axis or x axis, 90 degree or 45 degree. This is just an example. Now, let's do the reverse. So we'll do b plus a. So if we do b plus a, this is the final configuration we get to. Right? So if you compare these two, clearly the final configurations are different, which means that a plus b is not equal to b plus a. Right? So that's also telling you that finite rotations, even though they seem to possess both direction and magnitude, are not vector quantity because they don't satisfy this axiom that all vector quantities should satisfy. Right? So I say finite rotations over here because it turns out that infinitesimal rotations, which are very small rotations, do obey this property, right? And now that's something you will learn a little bit in detail when you take dynamics, all right? But for now, at least just remember that finite rotations, which are given by a non-zero or not a very small quantity, are not vectors, okay? Same thing with the electric current. You can think of electric current. You have two wires that connect, okay, at some point, let's say, and they are along the same direction, and the currents are moving in the opposite direction towards a common point. They don't annihilate each other, right? If you have 5 ampere going this way, 5 ampere coming this way, the resultant is 10 ampere. Just because these two wires are pointing towards each other doesn't annihilate the electric current. So that's another reason why electric currents are also not vector quantities. Okay, so that's good. So we understand what is the necessary condition and what is the sufficient condition for something to be vector. Let's try to understand how we can do math with them, because that's something we'll need to do, okay? But before we do the math with them, that is the algebraic formulation, let's look at the graphical representation, all right? So we'll look at the alternate representation of the vectors. We'll look at the alternate quadrant frame representation, which is very, very important because this is one thing that I find students struggle with quite a bit. So pay attention when I get to this. Magnitude and direction determination is just a matter of definition, how we add and subtract vectors, and how we multiply vectors, right? So those are the things that we want to look at. So graphical representation. Now, if you have a vector which has direction and magnitude, graphically representing it is not difficult. All you have to do is show it as an arrow. Okay, so if I want to draw, let's say, 55 miles per hour vector, which is pointing along northeast direction, right? So that's 45 degree from the east. All I have to do is pick a scale, right? If I want to really draw it, let's say using a ruler and a pencil, I can say, hey, I'm going to pick maybe 10 miles per hour as 1 centimeter. Then all I have to do is draw 5.5 centimeter long line, put an arrowhead over here, and draw it at 45 degree from east, right? And my job will be done. So if you had a graph paper or a piece of paper, you could easily do that. You pick your scale and you draw it, right? So the magnitude part is easy to do. Direction is something you can do with a protractor, or maybe you can use even a CAD tool to do this, right? Okay, so that's fine. So graphical representation is not a problem. But it is very hard to do any kind of algebraic operation with graphical representation of vectors. If I said that, hey, I want you to multiply this with a scalar factor 2 and then add maybe another vector to it and subtract another vector to it, you could do all that using graphical operations, but it gets tedious after a while because you don't want to really draw, right? I mean, we use math as a tool. We want to use math as a tool to make our life simpler, and that's what we want to do. So graphical representation is nice to look at, but doing math with it is very hard, right? Okay. Another property of the vectors is that the vectors that we deal with in this class are called free vectors. Okay? And why are they called free vectors? They're called free vectors because you can take a vector and move it anywhere in the space you want. As long as you don't change its direction and you don't change its length, which is the magnitude, you are not changing anything about that vector, right? So if I have this represented as a vector, I can move it anywhere I want in the space, as long as the orientation doesn't change. and the length of this doesn't change, it is still the same vector. Why? Because vector is defined by the length, the magnitude, and the direction. If you're not changing either of them, then the vector is not changing. Where the vector is situated, is located in the space, is not important. Now you might say, hey, that doesn't make any sense, because if I take, let's say, an object and apply a force on it, I could push on it, I could pull on it, I could apply the force at different places with the same magnitude, same direction, but the effect would be different. And that's perfectly right. The effect on the object would be different. But as far as the representation of that vector force is concerned, it's the same representation. Nothing is changing about that. Right? So don't confuse that with the actual outcome on the physical objects in the real world. Okay? Vectors we deal with are free vectors. If I take this and I move it around, as long as it's always pointing at 45 degrees from east or north, and the length is not changing, it's the same vector. So moving it in the plane, moving it in the space is not a problem. And that's why they're called free vectors. Yes?
So is there any kind of other vector, like you can move it wherever you want?
You can move free vectors anywhere you want.
So free vector you can move, but like
Right.
I'm asking, is there any other vectors?
Yes, there are quantities that if you move them around, they will change the essential property. But the vectors we are dealing with in this class are basically free vectors, right? So forces, moments, they're all free vectors, right? Okay, so let's talk about algebraic representation. Now, there are two kinds of algebraic representation that we deal with. One is polar representation. Now, what's a polar representation? Well, the idea with the polar representation is really very simple. So we know that a vector can be specified by both direction and magnitude, right? Magnitude part is easy. It's the direction part that we have to think about a little bit. How do we really specify the direction of something in terms of a number? Right? Magnitude part, we already have a number. How do we specify direction? Right? That's the main question. So if, let's say, I wanted to show this vector, I want to write this vector, velocity vector, in an algebraic way, I could definitely write the magnitude, which is 55. Now, for the direction, well, this is the direction, right? So how do I really pick a direction along that arrow? What I would do is I would pick what we call a unit vector. What's a unit vector? Unit vector is a vector that has unit magnitude, right? So I will pick a unit vector along this direction. Why a unit vector? Because, you know, it's the simplest possible vector I could pick. I could pick, you know, twice the length of unit vector, but it's pretty arbitrary. So just to specify the direction, if I can write a unit vector along this direction, which specifies the direction, then I can write the whole vector as the magnitude times the unit vector. So now this is encoding the information about the length or the magnitude, and E hat, which is a unit vector along this direction, is telling you what direction it is. But it doesn't seem very satisfying, right? Because what is E hat? How do we really write E hat? 55 is fine, that's the magnitude. How do we really write E hat, right? So this is what we call a polar representation. It's a very compact way of algebraically representing a vector. But I'm pretty sure that you have seen something else as well, right? So let's talk about that. And that's called Cartesian representation. So what is Cartesian representation? Well, Cartesian representation is written in a way so that you can write a vector in terms of unit vectors along some fixed canonical directions. So what you do is you pick two directions that are perpendicular to each other. Why perpendicular to each other? Because you want them to be independent of each other. And perpendicularity implies that that two things are independent of each other, right? So what you do is you pick two perpendicular directions. We'll call them x and y, okay? And what we will do is we will try to write this vector in terms of the vectors that go along x and y direction. Okay, and this is called vector law of triangle. So I can write any vector as addition of any number of vectors. Any vector can be written in terms of addition of any number of vectors. Here, because this vector is in a plane, which we are calling xy plane, I can write this vector in terms of two vectors that go along x direction and y direction, right? It's almost like saying that, you know what, here, this is a problem for you. You are here and you have to get over here, okay? And you are not allowed to travel along any direction except for horizontal and vertical, okay? So how do you get over here then? Well, you're only allowed to travel along horizontal and vertical direction, so you can go this way, and then you can go that way, and you will get there, right? Is that the only way you can get there? No, you could go up first, and then go towards the right, and you will still get over there. And all of these would be same. There will be no difference. Why there won't be any difference? Because if you go up this way, you are basically traveling along a vector which will be same as this. If you go this way, you'll be traveling along this vector which will be same as this. Why? Because both the vectors have the same length and same direction. They're free vectors, so you can move them anywhere you want, and nothing is going to change about them. Right? Now, if I said that, hey, you're not allowed, you can only travel along perpendicular directions, will this be the only choice available to you? So I'm relaxing the problem a little bit for you. So I'm saying that I want you to go from here to here, and you can pick your perpendicular directions. Will this be the only choice for perpendicular directions? Yes? No? No? What other choices can you take? Well, there are infinite number of possibilities, right? What you could do is you could say, hey, I'm going to pick this as my, perpendicular direction. I could say, this is my one direction. Let's call it x prime, and that's my other. And these two are perpendicular too. So to get from here, this is the origin, to the destination, I could go this way first. I could go this way first, and then I could go perpendicular that, like that. And I will get to the same destination, right? So when I pick these two as perpendicular directions, essentially I picked a different reference frame. Now, choice of reference frame is completely arbitrary. It isn't any different from picking maybe a certain unit system to express a quantity, right? You could express your mass in kilogram, in slugs, in pound mass. These are all relative. As long as you specify the unit system, people will know what you're saying, right? So if somebody wanted to really compare your mass with theirs, because that other person feels comfortable with maybe a size system, and you specified your mass in USCS, he or she could do the conversion to really meaningfully compare the two numbers, right? So the choice of coordinate system is completely arbitrary. Just because we show x and y like this doesn't mean that those are the only possible directions available to you. As long as you pick two perpendicular directions in the plane, you're fine. And you will see pretty soon in what situation picking maybe an alternate set of perpendicular directions to draw your vectors, to show your vectors, would be beneficial, right? So, okay, coming back to the Cartesian representation. So this is our vector. These are our canonical directions, x and y, right? So I can write this vector as a sum of this vector plus this vector. Now, we already know that any vector can be written as the magnitude of that vector times a unit vector along that direction. That's what we learned in the previous slide. Okay, so what we need to do is we need to specify what our directions are along x and y. Okay, and how do we specify the direction? By writing the unit vectors. So let's say unit vector along x direction is I hat, and along y direction is j hat. So in a three-dimensional coordinate system, you also have z-axis. Along z-axis, the unit vector is usually written as k hat. Okay, so I hat is the unit vector along x direction, j hat is the unit vector along y direction. So now I can write v1 and v2 easily, because I already have assumed the unit vector along those directions. v1 would be the length of this. And what is the length of this? Well, we have to do a little bit of trigonometry. This is a right angle triangle. This is 55, so this will be 55 cosine theta. So the vector v1 becomes 55 cosine theta I hat. And v2 becomes, which is this, 55 sine theta times j hat. Right? So those are the two vectors, and now I can write this vector v as sum of those two. So when I do that, this is what I get. So 55 cosine theta and 55 sine theta are called the Cartesian components of this vector. So Cartesian components are essentially nothing but the x and y components. Okay? So you have to pick your x and y direction, and then you can write your Cartesian components. So this is called a Cartesian representation. So given any vector, whether it's a velocity, acceleration, or force, if you know its direction and magnitude, all you have to do is do a little bit of trigonometry, drop the perpendiculars from the tip to the x and y direction, look at these lengths, direction you're moving in, and you got your Cartesian components, right? Okay, so let's look at an example. So we have already written v in polar representation as this, and v in Cartesian representation as this. Both of them are same vector, so they have to be same. So if we compare, you can see that the unit vector actually is nothing but cosine theta I hat plus sine theta j hat. Right? So that's the unit vector. Now, could you have written that directly after you learned about Cartesian representation? Sure. You know that this is the unit vector along this direction. The unit vector has magnitude as 1. So if you drop the perpendiculars, you'll get cosine theta here and sine theta over here, right? So let me draw this. and I'm going to do it separately over here to illustrate. So this is my velocity vector, and I'm just showing a unit vector, right? So you can see its length is small because it's unit magnitude, right? And this angle is theta. So if I drop the perpendicular, this would be equal to cosine theta, and this would be equal to sine theta. Why? Because the length along the diagonal is 1, right? So it's 1 times cosine theta and 1 times sine theta. So now I can write E hat directly from here as cosine theta I hat. Why? Because this is E hat, and these are the directions, plus sine theta j hat, right? This angle is theta over here. So once you know the Cartesian representation, it doesn't matter whether a vector is a unit vector or not unit vector. You can always drop the perpendiculars and write that, right? Okay. So let's look at another example. We have a force, which is also a vector, that's shown as of 5 Newton at an angle theta from negative x-axis, right? So this is positive x-axis, this is negative x-axis, this is positive y-axis, this is negative y-axis, right? Okay. So if this is negative x-axis, then this vector is opposite to this vector x. So if you have a unit vector pointing that way as I hat, then the unit vector pointing other way would be minus I hat. If this is positive j hat direction, then the opposite way would be minus j hat direction. So if I want to write this vector, how can I do that? All I have to do is find a way to get to the tip, right? And there are more than one ways. So I can go in the negative x direction like this, and then go in the positive y direction like that, and I can write f as sum of f1 and f2. Okay, so what is f1? F1 is nothing but 5 times cosine theta, that's the length, and this direction is negative I hat, so f1 is f cosine theta times minus I hat, and f2 is 5 sine theta plus j hat, right? That's the positive j hat direction. So you add them together, and you get your force f. Now, absolutely everyone in this class should be able to write any vector shown graphically like this in terms of Cartesian components, okay? And that's not something that anybody could say, hey, I didn't learn this in Mech 101. Okay, so let's talk about alternate quadrant representation. Like I said before, the choice of reference frame is pretty arbitrary. As long as you show what your reference frame is, it's fine. But you have to show it. If you don't show your reference frame, then it's a problem. Then we don't know what you're talking about. Okay, so just as you can say, my mass is 50, because you didn't specify the units, you can't write a vector unless you show the reference frame. Okay? So let's say we have our x and y direction, right? And you have unit vectors pointing I hat, j hat, okay, along x and y direction respectively. And I want to write this force F5 Newton, which is making an angle theta from x-axis. I can write that easily, right? We saw that. So we have 5 cosine theta I hat plus 5 sine theta j hat, and that's great. But now I'm saying, you know what? I don't want you to write f in this reference frame. I want you to pick a different reference frame. Okay, and new reference frame is the one that's actually pointing along this vector. So x prime, or the unit vector along this direction, is pointing along the direction of the force itself, and then the perpendicular direction is this j prime. Okay, so in this particular reference frame, how would you write the vector? Well, this vector is entirely pointing along I hat prime, which means that the force would be equal to nothing but 5, which is the length, times the direction, which is I prime. So if you pick that reference frame, there is no component along j prime direction, right? There's no component along j prime direction, and that's okay too. So if you show this reference frame and you write your vector like this, it's not a problem. Now the question is, what is the relationship between I prime and I? Are I prime and I same? No. Why are they not same? Because different directions, right? Is there anything common to them? What is common to I prime and I? Magnitude, right? By definition, unit vectors are unit magnitude, which means what is common to I prime and I is that they both have the same length, they have the same magnitude, but their directions are different, right? So I prime is not equal to I. It's a different vector. Okay, so where would this be useful? You will find that there are lots of problems where things have a particular or a preferred direction of movement, right? For example, if you take a block and you put it on an incline, right, then the block is only constrained to slide along this inclined direction. So if I was going to talk about the velocity of this block, I know that velocity would be along the incline, right? So Does it make sense for me to draw x-axis this way and y-axis this way and then resolve this velocity vector v along horizontal and vertical direction? It doesn't. I would rather choose a reference frame where I can write this velocity vector much more easily. So if I pick my x prime direction to be this, along the incline, then the velocity would be nothing but whatever the magnitude is times a unit vector along x prime direction. So you'll often see that we will pick alternate quadrant frame representation, and as long as we are consistent, we are writing all the vector quantities in that reference frame, we are fine. Right? You have to show the reference frame, and then you'll be okay. Now, that doesn't mean that you can't go from one frame to another. You can always go from one frame to another. Just as you can go from one unit system to another unit system, you can always go from one frame representation to another. Okay? So how do we do that? So let's say we have the same force of 5 Newton that's shown over here, and it's making an angle alpha from I hat and j hat direction. So I can definitely write this f in terms of I hat and j hat. It's not a problem. All I have to do is resolve this along this direction and this direction, and I'll be done. If I want to write this force f, let's say in I prime and j prime reference frame, I could do that too. All I have to do is find the angle this is making from I prime, and that'll be alpha minus theta, right? Alpha minus theta, and I can write that as well. Okay, so if you do that, you will get this equation, right? 5 times cosine alpha minus theta I prime plus 5 times sine alpha minus theta j prime. But if I said, give me the relationship between I prime and I and j prime and I and j. So essentially I'm saying, can you write the unit vectors in terms of the other unit vectors? That's essentially what I'm asking, right? This is a unit conversion, so-called unit conversion for the vectors. So if I have I prime, can I write it in terms of I and j? Sure, it's not difficult. This is just a vector. All I have to do is find the angle this is making from I, and I'll be done. So the angle it is making from I is nothing but theta. So I prime is nothing but cosine theta I plus sine theta j. Right? And what's j prime? J prime is this. So what is this? What is the angle j prime is making from j? If this is theta, this is 90 minus theta, then this is theta, right? So this angle is theta, so this would be equal to 90 minus theta, and since this is 90, this is theta, right? So the angle that j prime is making with j is nothing but theta. So that means that if I resolve j prime, it will be cosine theta along j direction, and that's this component, and the other component will be pointing towards negative x, and that will be nothing but sine theta along negative I hat direction. So that's what we have. Okay, so this is the sort of stuff that should be clear to everybody. So if you don't understand this, now would be a good time to ask. Yes.
Would we ever have to use alternate coordinate frames?
Absolutely, yeah. You may be given 2 coordinate frame, and you may have to go from one frame to another. But it's not difficult because you can always write unit vectors in terms of other unit vectors. And those of you who are playing with your phone right now, you will rue this missed opportunity because nobody will explain this to you again. Seriously. And you know who you are, and I know who you are. So I'm smiling, but actually I'm very angry inside. So when you're here, don't do that. Question?
Could you explain again where the thetas come from, like where you drew in the theta and the 90 minus theta?
So this is theta, right? This is 90 degrees. So how much is this angle? This is 90 minus theta, right? And this angle is also 90 between I prime and j prime. So that is theta. Has to be theta, right? Because this angle is 90, right? So if I draw this separately, this is I prime, this is j prime, and this is the j direction. This is 90 minus theta, which we just saw, and this is 90, so this has to be theta, right? Yes? Okay. Any other questions about this? Now remember, let me tell you something. I have a lot of patience with one-on-one students. So you can ask me the same question 20 times, and I will not hesitate to answer it in the class, but not on Piazza. So if you ask me a question that I've already answered here or I've covered, I don't have a lot of patience. Your fellow classmates could answer the questions on Piazza, but the prerequisite for answering a question on Piazza is that you come to the class and you remain engaged and you're paying attention. And if you're not here, at least you're watching the echo or looking at the slides before you ask a question on Piazza. So if I'm not answering your question, or if I simply say, please look at the slides and read the echoes, that means that I have probably talked about this in the class. Okay, so like I said, I have a lot of patience for one-on-one students. So if you don't understand something, feel free to stop me and say, hey, I didn't understand that, professor. Could you please go over it again? And I will be happy to do that. Okay, are there any more questions now? Hey, I'm smiling. All right, okay, so this is not difficult stuff. So if you're paying attention, I'm pretty sure that you're getting it. Okay, a few more things. Magnitude and direction of vector. Again, you may have seen some of this stuff before. If you're given a vector written in terms of Cartesian components, so this is the x component, this is the y component, right? A sub x indicates that this is a component that's along x direction, and a sub y is a component along y direction. Then I can talk about the length of this vector, the magnitude of this vector, by looking at these components, squaring them up, adding them, and then finally taking a square root. And that is called the magnitude of a vector. So that's the definition. So if I know the x and y component, square them up, add them, take a square root, that gives you the magnitude. The unit would be same as the unit of ax and ay. Of course, the x and ay have to have the same unit. They can't be any different. Example, if you have, let's say, force F given as 5i hat plus 6j hat, in Newton, you want to compute its magnitude, square each of these components, add them together, and take a square root, that'll give you the magnitude. You can also find the direction of a vector, okay, and that's easy, because if you have a vector f, and you are given the vector f in terms of x and y component, you know that f sub x would be this, and f sub y would be this, right? This will be the x component, this will be the y component. That's how you write this vector f. Then if you want to get this angle theta, it's a matter of applying the trigonometry. Tan theta would be equal to fy over fx, and if you take the tan inverse of fy over fx, you get the theta. Right? So this is easy to do. You can just take a y component, x component, divide them, and in your calculator punch in tan inverse, and you get your theta. Right? Okay, but you have to be careful about this kind of stuff. Why? Because sometimes, if you are not paying attention as to where the vector is pointing in the plane or in the space, you will get the wrong answers. When? So let's first look at the right answer. When do you get it? So let's say f is 3i hat plus 4j hat, right? Where is this vector pointing? Since x and y component, both of them are positive, it has to be in the first quadrant, right? Okay, so how do I get tan theta? Tan theta would be nothing but y component divided by x component, so 4 over 3. Theta would be tan inverse 4 over 3. You punch in the numbers in your calculator, you get theta. Now let's look at another example. So this is minus 3i hat minus 4j hat, okay? If you simply use the definition that I showed in the previous slide, where you divide the y component with the x component and do the tan inverse, the answer you will get is same as this, right? Why? Because minus 4 over minus 3 will cancel the negative sign, and you'll get theta as same as what you have over here. But you know it is wrong. Why? Because this force is pointing in the third quadrant. Why is it pointing in the third quadrant? Because this is minus 3, this is minus 4. Minus 3 means that x component is going that way, and minus 4 means that y component is going that way. And that means force F is over here in the third quadrant. And if you just simply substitute theta as tan inverse 4 over 3, your answer will come out to be something that will be maybe 30 degree, 40 degree. I don't know what the actual number would be. And that will be wrong, because it's not in the first quadrant. This vector is actually in the third quadrant. So what's the difference? Well, the difference is that it's actually 180 degree plus that angle theta, right? So if you draw that vector in the plane, you will clearly see it, what the direction is. So this is the y component, that's the x component, so that will be the angle. So if you want to give the angle from the positive x-axis, it's easy to do. All you have to do is add 180 degree, because that's the 180 degree, and you'll get your angle, right? Okay, so just be careful about these kinds of things. Magnitude is never a problem, because you square them. So even if it's a negative quantity, it becomes positive. You will never have a square root of a negative quantity. But with the direction, you have to be a bit careful. Okay, so let's talk about addition of the vectors. So some of the various algebraic operations we can perform on the vectors. How do we add them? How do we subtract them? And how do we multiply them, right? So addition part, let's first do it graphically. Like we said before, the vectors we are dealing with are free vectors. What does that mean? It means that you can move them anywhere you want in the space, As long as you don't change their direction, as long as you don't change their magnitude, they are same vectors, right? So if let's say I wanted to add 3 vectors A, B, and C, and we'll have to do this kind of stuff. So you'll be given parts and the blocks, and you'll be given multiple forces acting on it, and the question may ask you to compute the total forces acting on it, right? So since each force is a vector, you would have to add them up. How do you add them up? So graphically, it's very easy. So let's say we have 3 vectors A, B, and C, right? And I draw them in this XY plane. Now, the way I'm drawing them here is where I am sharing the tail of each of these vectors at the origin of the reference frame, right? They all have the same tail. But I can move them anywhere I want, right? So I could draw an addition of these 3 vectors by picking any vector as the first one. So let's say I pick A as my first vector, and then by moving the B in such a way so that the tail of B is at the tip of A, right? So I move B. So notice how B is translated from here to here. And it hasn't changed the direction, right? And I place it right over here. Then I can take my C, and I can move my C without changing direction and length and place it right at the tip of vector B. Okay? So now I have A, B, and C drawn serially. And if I want to get the sum of the 3, all I have to do is draw this vector from the origin to the tip of C, and that'll be the addition of the 3 vectors. So if you are careful about drawing this graphically, then all you have to do is draw this line, measure the length of this line, and measure the angle it's making from the x-axis, and you got your vector, which is A plus B plus C. What if I wanted to do, let's say, A plus B minus C? That'll be easy too, because A plus B minus C can be written as A plus B plus minus C, right? Minus 1 multiplied with the C. So when you multiply minus 1 with the C, what does it do to the vector? It flips its direction, right? So all you would have to do is you would draw A and B, and then instead of drawing C like this, you'll draw C that way, going away, right? Same line, but it will be pointing the opposite way. Then the sum would be A plus B minus C would be going something like this. Right? So graphically doing this is not difficult. And it doesn't matter which vector you pick first. So the order is not important. That's what we learned. Vectors should be independent. When you add the vector, they should be independent of the order in which you add them. Because if it was dependent on the order, then they won't be a vector, right? So I picked A as the first vector, but you could pick B first, and then add A to it, then add C to it. Your final answer will always be same. Okay? So graphical addition of the vector, not a problem. Okay, let's see what else can we do with the vectors. We can multiply vectors. We can multiply vectors with numbers, scalars. So what does it do when you multiply a vector with a number? So if I have a vector A and I multiply with a scalar number, a scalar factor 2, let's say, what does it do? If you multiply it with 2, essentially it's going to change the length of this vector by twice. So if this was, let's say, a 5 Newton force, you multiply it by 2, it becomes a 10 Newton force, but you didn't change the direction, right? Because you multiplied with a positive number. If you multiply with a negative number, it'll change the direction by 180 degrees. So if you multiply by minus 1, you will basically change the direction, right? It's still the same line, but it has flipped. It has rotated by 180 degree, right? If you multiply a vector with a 0, then the final vector you get is a 0 vector. Now, 0 vector is not same as the number 0. 0 vector is a vector where the x component of the vector is 0 and the y component of the vector is 0, while the 0 number is just a scalar. It's just one number. It is not same. So never write this equal to a bar equal to 0. That will be wrong, right? You see what I'm saying? So writing this is wrong. Why is that wrong? Because the left-hand side quantity is actually a vector, while the right-hand quantity that you're writing over here is a scalar. A vector can never be equal to a scalar. So the proper way to write a 0 vector is to put an arrow on top, okay? And that means what 0 vector means is nothing but 0 times I hat plus 0 times j hat. And that'll be important, you will see. Okay, how do we add vectors algebraically? Not difficult. All we have to do is write each of these vectors in their component form, right? So we have, let's say, vector A written as axi hat plus ayj hat, B as this, C as this. So we have x and y components of each vector. And if you want to add them together, you would take the I hat common, you would add all the x component, and you will add all the y components, and you'll get your final answer as that. Now, you can never add I hat with j hat. The reason is because I hat and j hat are independent of each other, right? So you are essentially think of I hat as apples and j hat as oranges. You can't add apples to oranges. You can add apples to apples. So these are all the apples over here, and these are all the oranges. Okay? Now, this is just for 2-dimensional, but this could be done for 3D or 4D, doesn't matter. You could have k hat component too, so you could have something like a z k hat, b z j k hat, and c z k hat, and you will add all the k hat components together. All right? So that's the basic thing. Question? What's the zero vector is a vector which has 0x component, 0y component. That's it. You will. So when I write, so pretty soon you will be writing equations like these. So I'll say, hey, this is what you need to do. Sum of the force equal to 0. Okay? This is the equilibrium condition. So those of you who have probably taken statics somewhere are probably already familiar with this. So we'll say sigma f is equal to 0. Okay? So when you say that, then on the left-hand side, you will have things like this. Sigma fx I hat plus sigma fy j hat. All right? So those are the summation of all the x component of the forces times I hat plus summation of all the y component times j hat equal to 0 vector. And 0 vector now you will write as 0 I hat plus 0 j hat. Okay? So when you do that, essentially, you are writing one vector equation, but this vector equation now will reduce to 2 scalar equation. So if you compare apples on the left-hand side with the apples on the right-hand side, what do you have? You have sigma fx here, and you have 0 here. Both of them are coefficients of I hat. So you can compare them. So sigma fx should be equal to 0, and sigma fy should be equal to 0 too, because this compares with that. See, if you wrote simply 0, you won't be able to do this comparison meaningfully. Right? So from a problem-solving point of view, you will need to write things in a proper way. Otherwise, you won't be able to go the next step. Okay, all right, so this is fine.